Good morning, students. Again, we're enjoying our nice springtime weather. So as I was told when I moved to this area, never worry about the weather because it will change. And that has probably been the one constant that we've always relied upon. Constant, no pun intended, constant of integration. Uh, what we want to do today is to continue the work with series. I referred now to our power series as functions in the interval of convergence. They behave like functions. And we see that the connection to the power series is basically the arithmetic of STEM. We have wonderful technology which can compute functions, values of functions quickly. That is, the arithmetic of the calculus is what the technology can capitalize upon. And computers do arithmetic really fast. And so that's an elegant thing. And so what we're doing is today is to continue that discussion and to make this more real for you. The Calculus 1 and Calculus 2 courses are essential for STEM education. And the main thing about this is that you learn more important mathematics in these two courses than you do in anything, and you will apply them over and over and over. So I hope that this is illuminating for you. It's actually nice to be studying something that you're going to use for the rest of your education. So what I want to do is look at an example. We're going to do several examples today and try to tie in some techniques that are important, just like when we were doing the integration problems. We got to the point to where, okay, ladies and gentlemen, we have tabulations of integrals, we have integral tables. And so what we want to do with the series is develop enough understanding, and then we can actually make a list of fairly popular series. Just like with integrals, some integrals are quicker to do than others. Series are the same. When they have nice behaved derivatives, we can move really quickly. Or if we can see a pattern, we can move quickly. So we're going to do basically the same thing today. But first, what I wanted to do was, again, capitalize on the geometric series. Now, I want us to recall the following formula. That is, every time we do an example with the geometric, we have to basically figure out what the actual series is. That is, when we have a series, how do we motivate it in a way that it's going to give us a nice formula? So one of the formulas that I told you about, we had this one. Remember, we have 1 minus r, so we're going to think of 1 minus x. So this suited the sum of the infinite geometric series exactly, where a was 1 and r was x. So we had a divided by 1 minus r. That's the formula that we derived at the beginning of chapter 9. And so we remember this was 1, so a, and then we have a times r, which will be x, and then a times r squared, etc. Now this, though very simple, it's extremely important. And so, of course, if we wanted to, we could go ahead and just write this with the summation form. Again, I'm reviewing this because these are important series that come up over and over again, and we want to capitalize on them. So this would be one that we could put in a list or a variation of this. And then, of course, for the convergence theory, we knew that the absolute value of r must be less than 1. So we would say for convergence, we would have this. So again, with our power series, we were looking for intervals of convergence using the radius of convergence and then checking the endpoints. With the geometric, we don't have to work as hard if we know we've started with this. Now, the other one that was of use to us, just to review, say we had the 1 plus x. So what I'm trying to do is show you how we're going to manipulate the next example, which is going to take a little bit more algebra, but it'll be doing the same thing. So this reminds us of this. So we want to fit the pattern of this standard series here. So we just put in 2 negatives. Again, this is something I've talked about before, but now I really need to hit home with this so you understand this construct. So we don't have to start over. We now know that we have an A of 1, and then we have an R of the additive inverse of x. So we can just run over here and replace the x with the negative. So we have n equals 0 to infinity. So we have negative x. Well, let me not put a -1. Let me just put negative x. That's a little bit. I'll flesh this out with the -1 to the n power. So now, just like we did last class, we'll just write this as a -1 times x, which maybe I should have just left it that way, but let's just go ahead and go with this. So now this will be -1 to the n, x to the n. Again, with the negative x in absolute value being less than 1, so we get the same interval. Now, of course, you're thinking with this, if we move things around more, we can shift the interval, just like we've seen before with the function transformations. You can shift the interval, you can stretch it, you can compress it, all these things that we do with functions in college algebra. So with this in mind, again, I didn't want to just jump into this example and not remind you where we've been. Here's an example. So what we're asked to do is compute a power series. Now you already know, I've told you already 3 times or more that the convergent power series is its Taylor series. So if we were going to work on this computing Taylor coefficients, we get the same answer, but we find this to be a little bit more direct. And also, with that said, if we don't have an alternate procedure, we can always go to the Taylor coefficient. So you always have options with these problems, just like you do with integrals. So compute a power series of f of x. Now, of course, if we're going to use this, it's going to have to look similar to this, or maybe with derivatives. You know, with derivatives, we can always, differentiating a power series, we can always work that to our advantage too. So we have 3 divided by 2x minus 5, and we want to center, or centered, at c equal 4. So that's going to be the expansion point. Now, the reason I want to do this is that I want to introduce the standard technique for doing this. We can clearly rig this to be geometric, but the way we do it is we want to go ahead and input the new center and then clean it up to get the 1 minus r. So move all the extra to the side and get that 1 minus r, and then we know exactly what r is and we're good to go. So first, introduce the 4 here. So we're going to say f of x, we'll start with this 3, 2x, and if you like, we can go ahead and write the -5 first. So just go ahead and recommute, so to speak. So we're thinking along these lines here. Let's introduce the 4 and the -4. So we'll get plus 2, and we'll have x minus 4 plus 4. So we're just doing the smoke and mirrors. We need a center at 4. So we need a -4, but then of course, just like doing integrals, we have to pay for it. So that's going to help us out. So again, when you start problems like this where the centers are changing, do the center first. Now let's clean this up. So we have a -5, and now we've got a 2 times an x minus 4. And then we have a 2 times a 4, so that's plus an 8. So the first time you do this, or with anything, put in all the steps to be secure. And so now we can run this up. We have the 8 plus the -5 will give us a 3. And then we have 2 times x minus 4. Now, this is looking pretty good, but again, we're going to need a minus. So the first thing we're going to do, and we need a 1 too. So we're going to factor the 3 to get the 1, and then we'll worry about the minus that we need. So we have a 3, and here we're going to factor the 3, and that's going to be a 1 plus a 2/3 x minus 4. Now, when you look at this and you think, okay, well, the 3's are going to absorb, which is fine. And now when we compare up here, we're almost good. We've got the plus. So to get the minus, we have to put in 2 minuses and then bracket things. So the 3's go away. No problem with that. Less clutter, right? So we have 1 minus, and we're going to have a negative, as we say, 2/3 x minus 4. So the idea here is that we put in the 2 negatives to get the negative here. So it's like we're here at this point, and then when we get to here, we've matched this. So when we look at everything that we have, we're like, okay, well, and here's one thing that's kind of interesting about this. When you think about the idea of doing these types of computations, and you consider the type of work that we have to do, think about it this way. Just look back through here and look at what we've done. When we start here and we introduce the -4 that we're going to need for the center, we subtract 4 and add 4 to get this. And then we clean it up. So we have 2 times x minus 4. And then we have the 2 times the 4, which is an 8. And so we have the 8 plus the -5, which is the 3. And we're left with 2 times x minus 4. Now, when we look at this, we're thinking, okay, well, let's go ahead and factor. Let's make this look like this. So let's factor the 3 out of both of these terms. So that's going to give us a 3 times a 1 plus a 2/3 times an x minus 4. So of course, when we multiply back through, we get exactly this. And now we want to introduce 2 negatives. The 3's go away. And when we look at this, we're good to go. That is, we have 1 minus a negative. So now when we look what we have in here, we're thinking, okay, this is what we call the new R, so to speak. So when we go up here and we compare, we see that this is the new R. So just kind of like right here, new R. And of course, the A is 1. So now we can go to here. Or we can just do this and rig it so that you can see the -1, the alternating. So now we get the series. Again, we've matched this. We have now -2/3 x minus 4 to the n equals 0 to infinity. So we just have this pattern here. And then we move to here. So you can always break this up. So this will give us now the series n equals 0 to, now we've got the negative here. So that's the alternating, the -1 to the n. And then we have 2 to the n over 3 to the n. I'll just write it like this, 2 to the n, 3 to the n, and then we have the x minus 4 to the n. Now, when you look at this and you think, okay, well, this looks neat, this looks good. So when we finish with this, we're thinking, okay, here's our series. Now, do you want to write it any differently? Do you want to make it look any differently? No, this is fine. This is exactly what we need. Sometimes students like to put everything, you know, like in this kind of package. Let me just write it this way. It's your choice, but this is fine. We can just kind of move everything into one fraction. And then just do a longer fraction bar like this, if you like, your choice. So when you look at this and you think about this, you're like, well, that was easy. I mean, the thing is that every time I teach analysis or topics in calculus, I think of different ways. As I do my own research, I think of different ways to talk about things. And you know, when I was thinking about presenting this, I thought, well, let me make this a little bit more clear for my students as to the pattern that we're seeking. And of course, this is very restricted. I mean, if we don't have the ability to transform this into this, then of course we can't use this technique. But now we want to see, okay, can we get an interval of convergence? Do we have enough information to do it? Absolutely, because we can use the new R right here. So what about interval of convergence? Sometimes, ladies and gentlemen, the interval of convergence is difficult. It really just depends what the building blocks are. And you know, we take what we can get, hopefully. So now the new R, so we've got what? Negative 2/3 x minus 4 in absolute value must be less than 1. So we don't have to do the fancy radius of convergence and all of that. We don't have to do that. We have the geometric series here. So we'll just, you know, we'll just use it. So this will mean what? So we have 2/3 x minus 4 less than 1. So now, if you will, we can just multiply by the 3/2, or yeah, multiply by 3/2. And now rewrite the conjunction, just using basic college algebra. You'd be surprised how many students can't do this. I don't know what happened, and it's okay. I don't care what happened. You need to know how to do this now. Now let me move Professor Ron over here because I'm getting all these grid marks again. Sorry about that. Let me just run through them and get rid of them. I have to have enough room to get to the focus so you can see what I'm doing. So now when we look at this, let me see if I can, there we go. Look a little bit better there. So now the conjunction, so we have negative 3/2 less than x minus 4 less than 3/2. Now we can just add 4 all through. So negative 3/2 plus 8/2 less than x less than 3/2 plus 8/2. So again, this will give us what? 5/2, if and only if. 5/2 x, and then of course 11/2. So now if you like, this will just be, we'll say x, if I write it like I did up here, x element 5/2, 11/2. Now one thing you can do when you look at this particular series here and you think about the endpoints. Now, lots of times if we do calculus or whatever, we can actually introduce cases where we include the endpoints. But let me just look at a couple of these to show you that we don't get anything new by doing this. But I don't want you to think that I'm just disregarding it. So here's what I'm going to do. I'm just going to move this here and show you that we don't just want to, look at this like, okay, well, I don't care about this. I think Professor Ron told us, so we won't worry about it. So what I'm going to do is I'm just going to copy this series right here. N equals 0 to infinity, -1 n, 2 to the n, x minus 4 to the n over 3 of the n. So let's just check these. Let's just check x equal 5/2, because like I say, there are times when we do certain calculus operations and we use this geometric technique and we actually include the endpoint. But let's just check this for good measure. So we have n equals 0 to infinity, -1 to the n. Now that we've used that, I'll just move this over. And so we have 2 to the n. And so now we've got the 5/2 here. So 5/2, and we'll just write this as 8/2 to the n over 3 to the n. And so now let's just reduce this. Now this is a real series. Now here, notice we're going to get what, 5. So this is going to be a -3/2, right? Well, we knew that. So now let's continue to reduce. Looks like we're just doing busy work, but that's okay. So now notice we have the negative here, which can come over and join this. This is a negative. So we're going to have a -1 to the 2n. And then we have 2 to the n. And we have 3 to the n. And then we have 3 to the n. And then now the new 2 to the n. So this is like doing the modular. This won't be a surprise to you. So now the 2 to the n's and the 3 to the n's all absorb. And of course, this is an even number. So this will always be a +1. So we get that series. And you don't need me for this. This will never converge because the limit of 1 is not 0. So this, when it's easy, right? So the limit as n approaches 0, infinity of 1 is not 0. So diverges by divergence test. So that divergence test is actually very powerful. And I've talked about this from day one when we proved the result. It's of immense importance. Now, the thing is, if you check the other endpoint, you get the same thing. So I'll let you do that. I'll just say check x equals 11/2. And let's see here, for 11/2, let me just go ahead and do it. I always tell you to do it. Let's just get some practice with this. That way you'll feel better about it. I demand a lot of you all, so let me just fill in the details. Just go ahead and do it. So we have -1, 2 to the n, and now we have 11/2 minus 8/2. We'll get the same calculation basically that are in here. Now, of course, a lot of times, when you're running out of time, you want to quickly check these, and so you can compartmentalize when you need to. But notice here, this is just the +3/2. So we don't get any addition to the factors here of the -1. So we get 2 to the n, so we get 3 to the n. We have the 3 to n here, and then of course we get another 2 to the n downstairs. So again, everything is absorbs except the -1 to the n. But of course, again, the limit as n approaches infinity of this oscillating generating sequence is not 0. So again, diverges by divergence test. So when I look at your work for the fourth test, I have no issue if you use, like if you use an integral table to do an integral. I don't have an issue with that. I like to see the technique. If you're using a series you already know, like here, instead of starting from scratch, if you use a series you already know, this is a valid technique. And I need to see some of this work. And if I don't see it, you're not going to get the credit for the 40% part that I'm doing now. Remember, ladies and gentlemen, that part of doing mathematics, actually an essential part of doing mathematics, is exactly what I do here every day I have lecture, and that is essential. And so I want you to be prepared when you move on. If you can't write your mathematics, then you're not prepared. That is not a personal attack. Everybody always says, my math professor's so mean. No, this is simply showing you what you need to be able to do so that you can move to the next level. That's what I'm trying to make sure that you understand. And it does not matter what you had before or whatever. You know what you need to do now. So own your work and give me enough information. Now, everybody, what does this tell us? Well, after you do all of this work, you're thinking, well, this technique didn't give us anything new. I mean, we pretty much knew that we're stuck without the endpoints here. And by doing this technique without any calculus involved, we didn't include the endpoints. So now we see the interval of convergence is unchanged from what we found initially. That is 5/2 to 11/2. We didn't add anything. So what happens in these cases when we do these function transformations, so to speak, is that we shift, we squeeze, we stretch, we do this just like you would normally do in a college algebra class. So we are doing function transformations just like you did in college algebra. So when I say to my classes, especially when I would meet face to face, I said, well, you learn pretty much everything you needed to know in this class in college algebra, except the trig. The trig's really important. And some of you all could benefit by attending my online pre-cal classes. I say that in good humor, but I rarely have Calculus 2 students that can do trig. And again, I think that's because you just maybe thought it was too easy. Trig, my friends, is very important. Ask my pre-calculus students. That's essential material. Now, what I want to do is to now think about how we can introduce some calculus. Say we wanted to actually find a series for a function if we have a nice integral formula where the actual integrand looks geometric. So I want to do just a general derivation here. So here's something we want to note. Observe. So any techniques that you learn, you can use. They're always valid. So let's observe the following. And what I did, I'm always writing down extra stuff. Not that extra stuff is always the best way to go. Let's see, I've got another example right here. So I want you to observe the following. We're going to write this as an indefinite integral like we were doing in the last class. Inverse tangent of x. We know what this is. This can be written as the following indefinite integral. Now, normally, like I said, I would choose like an x sub 0, but I'm going to be clever and pick something that will give us a constant zero. So this is a zero here. We know inverse tangent of zero is zero to x, and then we have 1 over 1 plus t squared dt. Now you learned that the first week, or unless you took a Calculus 1 class where they cheated and talked about these beforehand when they should have been doing inverse hyperbolic functions, but that's neither here nor there. This is a standard formula from Calculus 2 that you learned the first week. Now, when we think about this and we look at this, we're like, oh, Professor Ron, that you know, we can integrate term by term because we can rig that to be geometric. So what we want to do is produce basically a Maclaurin series for this particular function. Now, for the last one, notice, let's write this down. This is centered at 4. This is not a Maclaurin series. And if we did the Taylor series for this, it would look just like this, okay? But this was easier to do it with the geometric. So now when you look at this, you're thinking, okay, well, let's go ahead and rig this, how much easier this was than the last one. Now you appreciate the technique I just taught you. So this will be the integral 0 to x. And now we want to rig this. Let me go back to the first deal here. We want to rig this to look like this, okay? There's nothing difficult about this if you follow what I teach you. I'm not saying it's easy, but it is doable. So you're thinking, okay, well, we didn't have to do much work here except introduce 2 negatives. So now this fits the geometric. We have the a is 1, and we have the new r is negative t squared. So now we can go ahead and move this to the next level. So this is the infinite series, n equals 0 to infinity. Now we have negative t squared to the n dt. Now, of course, we can go, I should have just gone ahead and flipped these around already. Now we can interchange the integral and the summation. So now, of course, when you look at this, we've got the negative here and we've got the t squared, so we can pair it off as -1 to the n and then t to the 2n dt 0 to x. So now when you look at this, it's like, okay, well, that's add 1 divided by the new power. So we get the series n equals 0 to infinity, -1 n, just like we did last class, t to the 2n plus 1 divided by 2n plus 1, evaluated from 0 to x. Now you're going to see why I put the 0 here. Lots of text will just put the c out there, and then you choose a convenient value for x and work it that way. I do that too. Either way is fine. This is just an alternative way, maybe that you might find simpler. It certainly is maybe a little quicker. And so now we can just replace. So we have n equals 0 to infinity, replace t with x, so we get -1 to the n, x to the 2n plus 1, 2n plus 1. And now, of course, the 0 here, so we get minus this series, which is just going to 0 out. So here we have 0 to the 2n plus 1. So of course, when n is equal to 0, we just get 0 to the first power. So for all indices here, this is just always a zero term. So this contributes nothing. So we get a zero constant. So we get this. So we get a nice Maclaurin series. I'm obviously taking the polynomials and extending them infinitely because I already told you it was going to work. So why not just let the cat out of the bag? Otherwise, we just, walk around with blinders on. So now, when you look at this, we have a nice series for the inverse tangent. Now we're thinking, okay, well, do we get extra? Okay, so this is what I was talking about before. We're like, okay, so we used the geometric series and we did some calculus to it. What's the interval of convergence? Can we actually figure it out without a whole lot of work? And we can. So we're going to think first, we have our new R. So we have negative t squared absolute value must be less than 1. So let's just do a little bit of algebra. This is simple algebra. Of course, the -1 absorbs. So we get t in absolute value squared less than 1. Now, of course, we can apply the square root function, which is an increasing function, to preserve the inequality. So we get t is less than the square root of 1, which is 1. Again, I have students who can't do this. And if you have struggling with this, then you need to review it, okay? I'm at the point now where prerequisite knowledge has to be known. This is not something that you learn in Calculus 2. You should already know how to do this. But if it's rusty, then review it. And do not get mad at me if you mess it up. Again, ladies and gentlemen, these techniques are essential. So please take the time to do your work carefully. Now, this is a conjunction. So we get -1 less than t less than 1. So, okay, well, we kind of thought that. Do we include -1 and 1? Well, we looked at the last one and that was just a, no, but we needed to check. But like I said before, we've applied some calculus here. So there may be the possibility that we would include the endpoint. So we need to check this. So let's check them. So here's our series right here. So let me just go ahead and so we can see it. Let me just go ahead and put the inverse tangent of x right here. Put a box around that. Or a quasi box, not really a box anymore. It looks more like a fractal. So now we're going to replace x with -1. So we get n equals 0 to infinity. So I like to bridge these two sections together so you see how they're related and we get a really nice interplay between the series and the geometric constructs. So now you're thinking, well, this is easy. We like 1s and -1s. So we just get extra copies of -1. So this will give us a -1. So we have an n plus 2n, which is a 3n. And then, of course, plus 1. 2n plus 1. Now, like we've done before, we just need to know the parity here. We know, again, that 3n, or 3 is congruent to 1 modulo 2. So this is just the same thing as n plus 1. So we can rewrite this. So just say 3 is congruent to 1 mod 2. Remember, you do mod 2 pi with the unit circle, mod pi is the same thing with integers. So this is just -1 to the n plus 1 equivalently. But now, of course, this is good because now this does alternate. So now we can say, all right, well, the an is just the 1 over 2n plus 1. So we have, just looking at an alternating series, This limit is clearly 0. So the limit as n approaches infinity of 1 over 2n plus 1 is 0. And then we want to say, okay, well, what's the next element look like? Excuse me. So let's just go ahead and do some simple calculations. 2n plus 1 is less than, if we replace n with n plus 1, we'll get, here, let me refocus. When I move the papers around, it sometimes gets a little blurry. And then we'll have 2 times n plus 1 plus 1. So that's just what 2n plus 3, right? So these are clearly greater than 0. So let's reciprocate. So we get 1 over 2n plus 3. And that's a sub n plus 1. And this will be, when we reciprocate, less than 1 over 2n plus 1, which is a sub n. So this means that a sub n is non-increasing. So this is just the alternating series test. So this series converges. So we'll say series, this one converges by AST. So with this analysis here, we will include the -1, which we didn't in the previous. But again, we did some different operations here with the calculus. So we can't just assume that, oh, well, you know, it's geometric, we don't care about the endpoints. Well, we do have to care if we do some calculus, because that can change the convergence at the endpoints. Remember, the theorem doesn't tell us anything about the endpoints. It's just on an interval of content. Endpoints are always interesting in analysis because they're just separate cases. So for the next one, let's check n equal 1. Or excuse me, x equal 1. So here, let's just change that to a 1. So let's go to our series. This will be a little bit easier. So we have n equals 0 to infinity. And we've got what? -1 to the n. And then, of course, 1 to the 2n plus 1 over 2n plus 1. So again, we get another alternating series with the same proof. Notice here, we get -1 to the n. That's always 1, 2n plus 1. So it alternates just like this one. So by same proof, series converges by alternating series test. Again, it alternates. The a sub 1 or a sub n is the same. We do the same proof, no different. And so now, lo and behold, we do include the endpoint. So interval of convergence will now be including -1. So we use a bracket and including 1. Now, like I said before, this would be a series that is normally included on a series list as a popular series. And notice this has an interesting look to it. Let's just look at it a little bit, and then we'll work on another example. So when you look at this, you're thinking, okay, here's the series. Let me just write it down again. So we have -1 to the n, x 2n plus 1, 2n plus 1. And this is inverse tangent. And we have an interval of convergence, that is x lives here. So now we can let n equal to 1. Well, let's do n equals 0. Sorry, let's just write down what we have here. So let's write down a few terms. So n equals 0. So we're going to get -1 to the 0, x to the 0 plus 1 over 0 plus 1. And then let's look at the next term. We have n equals 1. So we have -1 to the first power. So x to the what? 2 plus 1 over 2 plus 1. And now n equals 2. So we have -1 to the 2. X, now we'll have a 4 plus a 1. So that's 4 plus 1. And downstairs, 4 plus 1. Well, let's just do one more, just to see what it looks like. And then we have n equal 3, -1 to the third power, x. So we get 6 plus 1. 2 times 3 is 6. 6 plus 1, etc. So what we're seeing here, inverse tangent, will look like this. So now notice this will just be x divided by 1. So we get x. Now we have -1 to the first power, which is -1. We get a cube and a 3. So minus x cubed over 3. And now here we've got a -1 to the second power. So that'll be a plus. So we have fifth power, x to the 5th divided by 5. And then, of course, -3 to the first. So it's going to alternate, obviously, x to the 7th, 7. So this will be plus, minus, etc. So this inverse tangent has a really interesting progression here. And so if you use your ebook, they'll love the ebook to this class. You have your series for the arctan right here. So it's in, here's the interval of convergence, and it's considered one of the good series, so to speak, of elementary functions that you need to know. So this is a list that's talking about series we've already discussed. So this is kind of like an integral table when you consider what we've done before. So again, when it comes to the series, we can think of this computation like we do with the integrals that we've done. Now, let's look at an example, another example that has to do with a tangent function. But before I do that, I've got one more example I want to do here. So let me move this out of the way, get some clean paper. Let's see here. Here's an example that's going to involve some derivatives. So let's do this one. This will be fun. It's easy though. It's not hard. I've got all kinds of examples here. So I'm trying to bridge all of this together so you can get some nice synthesis of this. Here we go. So now, here's another example that will capitalize on the use of the geometric and some calculus like we did in the last one. So with this last problem that I've done, if you have a WebAssign problem, ladies and gentlemen, well, okay, if you have inverse tangent of something besides x, just replace the something besides x in the series we just computed. And boom, you got it. And then you might have to adjust your interval of convergence because maybe you shrank it, expanded it, or you did a compression. Okay, so the idea is that once I give you an infinite series that for a particular function like the geometric, use it. You don't have to start from scratch. I don't want you to start from scratch. I want you to use what I teach you. But anytime you're in doubt, you do a little bit more computation so you can, build your confidence. Okay, so and that's a big hint with your WebAssign. So that was my hint for you. So now let's do the same thing with the geometric, but let's do some derivatives. So what we want to do is write a power series. I think you have to admit that this is fun. This is fun work. It's like working on integrals, but even better. We're getting to do some nifty arithmetic. So now you know why your calculators work. What is calculus? Sophisticated arithmetic. write a power series for f of x. So we have to do some derivatives here. 14 divided by x plus 1. Like, oh, here we go again. And let's see here. Yeah, this is going to work. We have a cube here. So we're going to have an x plus 1 quantity cubed. Okay. And the thing that we want to note here is that this isn't geometric in that it, we don't have, the a over 1 minus r, but we know if we start differentiating things, then we can rig it. So here's the trick. Use geometric, and then we can make some adjustments if we need to. So of course we observe, and you're thinking, can I just do some substitutions? Absolutely you can, but if your series doesn't have this form in the chart, you can't use it. So we gotta do something different. Now let's observe the following. 1 plus x. So we're looking at the 1 plus x there and thinking, okay, let's do some derivatives here. What does this equal? Well, this is from the very first part of the lecture, just to remind you. This will be n equals 0. Remember, we have to put in the 2 minuses to rig the geometric sum. This is -1 to the n, x to the n. And we know that this works here. So we're thinking, let's just go ahead and work with this. So first, let's write this way. So we're going to start out with 1 over 1 plus x, and we're going to differentiate it, but we're going to be lazy. We're going to write it with the negative power. Don't you like the prime notation? I mean, the Leibniz notation is so beautiful and elegant, but boy, the primes are so nice and quick. That's what Newton did. Newton loved this shorthand notation. All of his physics work was done with the shorthand notation. Leibniz gave us the more usable differential. I mean, we needed Leibniz, but Newton just surged with this. So when we differentiate this, we get a -1. Well, let me write that as a 1. I started to write an x. 1 plus x to the -2, okay? So now when we look at that, we're like, okay, well, that's going in the right direction. We need a -3. So let's try it one more time. So we're going to do -1 plus x to the -2 and another prime. So now we get the +2, 1 plus x to the -3. So this gives us 2 over 1 plus x cubed. So when you look at this, you're like, okay, well, we can do this because we can do differentiation, term by term differentiation of this series to rig this. So now we got it. So let's do it. F of x is 14 times this. This is, let's just write this, 14 times 1 over x plus 1 cubed. We'll just write it as 1 plus x now since we like it that way. And so this is going to be 7. We've got a factor of 7 that we need here. 7 times, I'll use the Leibniz notation now, the second derivative of this guy. So what we have to do, just like with the integrals, like I did before, we have to set up the calculus. So 14 over 1 plus x cubed is really 7 times the second derivative of 1 over 1 plus x, which we've just shown here. Constants moving in and out as we need. And so now we're thinking, okay, well, that's an infinite series. So we replace here and we're going to differentiate twice. So this is going to be 7 d dx. So we'll just move one of the derivatives inside. So we got this one, -1 to the n. Take the derivative, bring the n down, x to the n minus 1. So we replace this with the series and differentiate it once, term by term differentiation. So n down, subtract 1. So now, of course, if you wanted to, you can start with 1 here. We won't worry about it. We'll just fix it at the end. Now we need to do one more differentiation. So we have 7. Now pull the derivative inside, do it again. And we got an n here, sorry. Need that n. So we have 7, n equals 0 to infinity. Now run the derivative inside one more time. Take another derivative. We have -1 to the n. And now we have n times n minus 1, x to the n minus 2. So when you look at this, you're like, my goodness, this is easy. I mean, there's nothing to it. The integrals were so much harder. But now notice, differentiate once, differentiate again. So now let's just go ahead and work with this. We see the first n equals 0 and n equal 1 just zero this out. So we can really just start at 2. We're not re-indexing yet. Let's just start at 2. So this will be the series n equals 2 to infinity, because the 0 and the 1 don't give us anything. And then we get what? 7, -1 to the n times n minus 1 times x to the n minus 2. Now, when you look at this and you think, okay, well, what do we want to do with this so it, looks easy or whatever? This is fine. This gives us everything we need. This is a series that works. Notice when we write the series, we want it to be something that's going to look easy to use. And notice, just like I said before, as we differentiate here, we can see here that with the differentiation, as we use the power rule, we just develop 2 terms here that don't give us anything. So we're just like, okay, if we start at 0, then that's 0, that's gone. And if we start at 1, then that zeros, and that's gone. So now we just start the sum at 2, and that way everything is non-zero. So we have n equal 2 to infinity, 7 times -1 to the n, just bring the 7 on inside, n times n minus 1 times x to the n minus 2. Now, if you want, you can re-index this. It's no big deal. If you want to re-index, you can. Now, let's just notice, at least here, we have -1 to 1. Do we include the endpoints? Let's check. So check x equal -1. So we have n equals 2 to infinity, 7, -1 to the n times n minus 1. And now we have -1 to the n minus 2. So this will give us n equals 2 to infinity. Now, of course, we have the -1, so that's going to join this. So we have 7. We have -1 to the 2n minus 2, n plus n minus 2, times n minus 1. Now, of course, what we notice here is that when we've got all these 2's here, this is always going to be a even number here. So this is always going to be a positive 1. So this is just like mod 2, this is a 0. So this is always a 1. So just remember, 2n minus 2 is congruent to 0 mod 2. How interesting. So this is just what? The integral, the series n equal 2 to infinity of 7 times n minus 1. Well, that's going to be a really bad issue because we see this this does not have limit 0. So now we see limit as n approaches infinity of 7n times n minus 1 does not equal 0. So in this case, series diverges. Series diverges by divergence test. So that's not a surprise. So we don't include -1. What about 1? Well, I think you'll see it's the same thing. But I want you to be able to check the endpoints. So now we can see that in this case, this just becomes a 1. So we have the series n equals 2 to infinity, 7, -1 to the n times n minus 1. And now we have 1 to the n minus 2. But now that's just a 1. So this gives us n equals 2 to infinity, 7, -1 to the n. Again, that just being 1, n times n minus 1. Now, of course, we have the same deal going again. This does not have limit 0. It oscillates. So limit as n approaches infinity of 7 times -1 to the n times n minus 1 does not equal 0. So series diverges by divergence test. And so unlike the integral operation we did, we don't get anything new. So now interval of convergence. So here we've got our new series. I'll just go ahead. This equals 14 over x plus 1 quantity cubed right here. And we see that the interval of convergence doesn't change. So we'll just say interval of convergence -1 to 1. No change. We don't add the endpoints because in both cases we get divergence. Now, and a lot of times this is a quick test, but we saw with the arctangent that it was very important. I guess either way it's important. I mean, if you don't include it, that's essential. If you do include it, that's essential. So the idea here is that we're not trying to just take on extra work, like, okay, let's just do more work because we don't have anything to do. We need to make sure that we have the actual interval of convergence. And we know there are 4 cases, can be including the endpoints, not including them, or one or the other. So that's what we need to determine. In some cases, it's very difficult to determine. So don't always get upset when the analysis gets, really difficult. Sometimes it can get insurmountable and we have to try other techniques. Now, what I want to do is look at some examples. So now what we're thinking, we can use the geometric series, rig it to get a series. We can use the geometric series with integration. We can use the geometric series with differentiation and create series. So the beauty of this is that should let us know something. That is, if we keep doing this and we're like, okay, well, we're happy with this, this is good. Can we always do this? No. But before we actually finish this, I want to just do a couple of other examples having to do with some approximation. Now, notice when we have these new series, we can say, okay, well, let's use them to approximate some things and to a certain degree of error like we've done in many previous examples. So let's go back to the arctan. Now, of course, once we develop a series, you can use it, and you can always look in your ebook here to utilize a series to help you move along, okay? So print this out from your ebook. It's very useful. So now here's an example. That is, let's go ahead and use something we already know. Approximate inverse tangent of 1/4 with error less than 1/1000. So now we're thinking, okay, well, we can do this because we know what arc tangent looks like. So we know inverse tangent of x, we just derived this, n equals 0 to infinity. And of course, the infinite series work for the geometric ones, even though, I mean, when you think about it, ladies and gentlemen, the power functions are easy for calculators to work with, okay? Because they're just the basic operations. Calculators do that very well. And then, of course, we're gonna, the king of all series is the binomial, which we'll talk about next week, and that'll be interesting. So we had -1 to the n, x to the 2n plus 1 over 2n plus 1. So when we think about this, we've got a value for x. So this is alternating, and we just want to look at the first neglected term, so to speak. So let x, and we've done this before, this is old hat, 1/4. We keep doing the same thing over and over, but hopefully you'll remember it. So now we can look at what's going on here with the first neglected term. And if you want to call it, you can call it u sub n plus 1, since we're going to kind of throw everything together. So we'll look at the absolute value of the first neglected term. So we'll say u sub n plus 1. Sometimes we use the a sub n plus 1, but I'm just going to throw all this together and call it u sub n plus 1. You use your favorite letter. And so we have -1 to the n plus 1, and we have 1/4 to the 2n plus 2. Well, in this case, it's going to be 3 because we're going to have 2 times n plus 2, or excuse me, 2 times n plus 1 plus 1, so that's 2n plus 3. All right, I've done this before. We'll have 2 times n plus 1 plus 1, which is 2n plus 3. So we get that. And then downstairs, we have the same thing. We're going to have 2n plus 3. Same argument. Okay, so now when we look at this, the negatives will absorb, and we've got these hanging out. So again, when we do the absolute values, we have -1 to the n plus 1. So that will always be +1. And then, of course, we have what's left over. We have this that comes downstairs. And these are all positive. So we have 1/4 to the 2n plus 3 times 2n plus 3. Now, the idea here is that when we look at this, we're going to have to test again and just see what gives us the sufficient. That is, what's the least one that will work for error of less than 1/1000. So when you look at this part here, notice this will equal, that's 1. So we have 1/4 to the 2n plus 3 times 2n plus 3. And we want this to be less than 1/1000. So you're thinking, well, this power is getting big kind of fast, so maybe we don't have to be too crazy. You know, we want the first term. And so again, when we look at this and we think about what we're doing, we just need to figure out how many terms we need. Now, when you think about this and you think about what we're doing, as we've done before, we tested. So let's just go ahead and test, and maybe we can hit the jackpot. Let's try n equal 2. That might be too big, and we'll have to go down some. So in this case, we have 1. So let's test. We have 1. And so now with 2 here, we're going to get what? We're going to get a 7. Well, first, but you know, before we do all of this, let's just go ahead and reciprocate because I don't like all these fractions. Let's just go ahead and reciprocate this. So this is just going to be 4 to the 2n plus 3 times 2n plus 3. And we need this to be what? Greater than 1,000. And so now we have what? 4. So we have 2n. That's going to be a 4 plus a 3. And then a 4 plus a 3. So this equals 4 to the 7th times a 7. Now when you do this, that's just going to be what? 64. I mean, we've got 3 copies, 3, 3. So 64 times 64 and times a 4 times a 7 times a 28. Now I actually computed this and I got 1,000 or 114,688. The idea here is that that's really good. I mean, that's more than we need. So this is like good, but maybe more than we need. So let's check n equal 1. So we'll have 4, again, 2n plus 1. So that's going to be a 2 plus a 3, which is a 5, times 2 plus 3, which is a 5. And in this case, we're going to get, let's see, we've got 3 copies and 2 copies. So that's a 64, and we've got a 16 and a 5. So 16 times 5 is 80. So 64 times 80. We can actually do this in our head. So that's going to be a 2 and a 3. So that's a 512, right? Now, let's see. So here, when we've got the 80, so let's see, we've got 2 and then the 3, 512 and a 0. And that's even better. That's good. Now, when we think about this and we think about n equal 1, let's just look at this and say, what does that mean in this particular case? So if we look at this particular setup here, the partial sum that we need is S1, but we start at 0. So this basically says we need n equals 0 and n equal 1 terms. Because we're starting our series at 0, we have to keep that in context. We need these terms. So this implies that inverse tangent of 1/4. I like this analysis. It's just easy arithmetic, but the key here is that when we think about doing this type of work, we just have to, again, look at what the arithmetic is telling us. And so now we've got what? N needs to be at minimum 1. So that's going to give us 2 terms. So let's go up here to our series. So we have, in this case, when n is equal to 0, we get 1/4 to the 0 divided by 1. So this is just, and of course, that's 1. So we get 1/4. So this is n equals 0. And now we need n equal 1. So let's go up here. Let's just write it out. Plus -1 to the first, 1/4, again to the third, divided by 3. So this gives us 1/4. Now we've got minus, and then we've got a 64. So we've got a 3 times a 64. 3 times a 64. So, oh, good. So that's easy. So we've got what? 3 times 64. And so 4, so what? Let's see here. So 4 into that, that's going to give us 16. 16 times 3 is like 48. I approximated this with Google, but I'm just doing exactly now. And so now minus a 1, right? And so what, 3? So we've got 47. And then we've got what, a 2, and 18 plus 1, 192. So that will be an approximation that will be good to 3 decimals, an error of less than 1 over 1,000. So again, the work we do is the same. Sometimes students just start, adding. Sometimes I've done this where you just start adding terms and seeing, what kind of result you get, how it improves. But if we have this alternating series and we just use the first neglected term theorem, then that makes this process a little bit easier. And so now when you approximate this, I did use Google here to 3 decimals. This will be approximately 0.245. This is exact, and this will be my Google approximation. So all of this is the same as we've done before. It's just a little bit different setup where we focus on utilizing the first neglected term without having to do a lot of extra arithmetic. All this arithmetic that we do is just basically the test. This is really good, but that's too much. That's too much. And so we're thinking that that's even better. But if WebAssign just says we just want, the least n, then we need to look for that. Now, one type of argument that we want to do again involves the natural logarithm, and I want to look at that. So again, this is just like we've done before. This is nothing new. We just have a power series here, just like we did with the Taylor polynomials. It's the exact same calculation, really no difference. Now, there was an example here. I looked through my notes where, again, we want to use a famous function to sum a series. So let's produce a famous function. Now, when it comes to working with particular functions that we dealt with, I want to emphasize the fact that when we come up with something, we may have to rig it a little bit, but the rigging is not a problem. So when I go back to an example, we're going to actually do one with a tangent just to kind of mix it up a little bit. But I want to look at an example where we do another derivation. And I'll just say, here's the example, and here's what we're going to do to figure it out. The example says sum the series, and you're going to look at that and say, well, I don't really know what to do. Doesn't look like arctangent. So sum the series. So we have n equals 1 to infinity of -1 to the n plus 1 times, so we've just got, put a little dot here, just write it like this, 3n times n. Now I'm going to flesh this out a little bit so it looks more user-friendly. So we have -1 to the n plus 1. Make it look real user-friendly. So I'm going to bring this upstairs. So it's like an x raised to a power and then dividing by n. Okay, so that looks unfriendly, but that looks very friendly because you're thinking you can rig this. Now, what I want to do is to come up with a series that's going to help us do this. Basically, when it comes to writing a series, we're thinking we need an interval of convergence that will work for us. So let's do the same technique with the natural log. And again, you can do your rigging, like I said before, with the arctangent. So how can we do this? Well, we haven't come in contact with a series that looks like this. So we're going to have to figure one out. So observe. That's why I love these WebAssign problems. They really do make you think about this work. Observe, like we did for the arctan, that log x is what? Now remember, the natural log is defined, this is just calculus 1 right here, for positive x. So now when we look at this, we're going to think, well, let's pick a convenient x of 0 that zeros the log term, which is 1. So we're going to go 1 to x, just like we did in Cal. This is Cal 1. This is straight from Cal 1. 1 over t dt. This is the integral definition of the natural logarithm of x. And this has all the properties that you learned in pre-cal. So you look at this and say, well, we can rig this too, because we can make this geometric. So let's do it. So let me show you the rigging. So we get 1 to x, and we're going to add and subtract 1. So first, we're going to do, in this case, we're going to do something like this, t, and we're going to do a -1 and a +1. I could have done this separately, but let's just go ahead and work it out this way. So now we've got our 1 over here, and we've got plus a t minus 1. So we moved the center around. Notice this equals t, and now we're back to what we did at the beginning. We need to put the 2 minus signs in to rig it. So we have 1, and then we have 1 minus negative t minus 1. So now you're thinking, boy, we have a lot of negatives running around. Well, notice the negative gives us the t, and the negative gives us 1 with the negative minus 1. So this gives us the 1 over 1 minus r, which we need. So there's the new r. So what do we have? Geometric. So 1 over x. Now, this is the new r, so we get the series n equals 0 to infinity. Now we have the -1 to the n, t minus 1 to the n, dt. So if you remember, this is just what we did at the very beginning. Let me see if I can find that sheet. Oh yeah, right here, this one, the minus with this. There's the new x or the new r and the alternating. So exactly what I've done here, that. But x is replaced with what? The negative of t minus 1, so that gives us this guy. Okay, so nothing new. Now we can do the term by term integration. So we get the series, just like we did with the derivatives. So we get add 1 divided by the new power. So we get -1 to the n, t minus 1 to the n plus 1 divided by n plus 1, evaluated from 1 to x. Of course, now you know why I've chosen the 1. It's going to clean that out, give us a 0 constant. So now we get n equals 0 to infinity. So we have -1 to the n, replace the t with x, x minus 1 to the n plus 1 over n plus 1, and then minus the series n equals 0 to infinity. So we put in the 1, -1 to the n, 1 minus 1. This just helps us from having to evaluate the constant. I just kind of rig it so we've got a useful value of x from the outset. It works just as well. And of course, for all values of n, this just zeroes out. So this gives us just this. So we have this series n equals 0 to infinity. We have -1 to the n, x minus 1 to the n plus 1 over n plus 1. Now, again, when we look up here, we're thinking, okay, well, what's our interval of convergence? So let's check that. The new R, so to speak, is this. So we have negative t minus 1 in absolute value must be less than 1. So that gives us the negative absorbing, obviously, t minus 1 less than 1. So there's our conjunction. So negative 1 less than t minus 1 less than 1. So add 1 throughout. So that'll give us a 0. Obviously, not going to work as 0. Log of 0 doesn't make any sense. T, and then of course we get a 2 here. So there's no hope of ever including the 0. That's foolish. I mean, this clearly doesn't work at 0. And that's one thing about Taylor's theorem. If we show that the remainder goes to 0, then we actually know the series converges to this. Here we get it for free. I mean, let's think about this, ladies and gentlemen. We'll get this for free. This technique is really valuable. We don't have to worry about a remainder term going to 0. We can just leave that at the door. So now that's a wash, but what about 2? So let's check x equal 2. So now let's just go ahead and put a box around this. So now if we look at this, we've got what, x equal 2. So we have series n equals 0. I want to have you check the endpoints, like just finding the n for the error, just good calculations, easy to do, but important. So we have what, 2 minus 1, or we like ones, right? N plus 1. So that's just a 1. So we get n equals 0 to infinity of negative 1 to the n over n plus 1. But of course, now this is good because now we can just say a sub n equal 1 over n plus 1. And we observe that the limit is 0. Very easy limit. And then, like we've done before, this is clearly non-increasing. That's an argument we've done many times. A sub n is non-increasing. Certainly doesn't get bigger. And so this means converges, series converges by alternating series test. So we get a check there. So of course, like I said before, the 0 was a wash, but now this implies x interval of convergence will be from 0 including 2. So again, you know, when we do this calculus, we can sometimes add the actual endpoints. And this is actually one of the series, the ln of x is right here on your chart, right here. Boom, right there. So this is on your chart too. Of course, you get the sine and the cosine and the e to the x, but those are our friends. Those have easy derivatives, and we work with them all the time. So it's like, you know, if everything had nice derivatives like cosine, sine, and e to the x, then life would be just really a cakewalk. But we can't rely on that. We see that even if we get to use the geometric series, we still have to do a little bit of work. Now, what I want to do is say, okay, well, we've got a series that's moved around, so to speak. So now notice here, we just want to rig this. So we want 1/3. So here, let's just do this. So we have, notice this can be rescaled, re-indexed to match that. So let's just go ahead and re-index if you like. So we'll do ln of x equals, and we'll start at 1 to match that. Sorry, up there, start at 1. So we have n equals 1 to infinity Now that means we need to lessen everything. This we can just write as n minus one or whatever. It's got to alternate. So if we start with one, we can just write that as n minus one or n plus one. It doesn't matter. We just need to alternate. So when it's zero, we want one. So we're just going to say -1 to n plus one. You can choose any power for this, just so long as it coincides with the alternating plus and minus. We need it to start out plus, so I'll just put n plus one. Now, if we start at one, we made this bigger. We need to make that smaller. So this is x minus one to the n by one, and make this smaller by one. Now this matches up with this. So then we say, okay, well, we need 1/3 to equal x minus one. So add one, so x equals 1 plus 1/3, which is 4/3. So this is so easy now that we have the series. So now n equals 1 to infinity here. And I wrote it in the user-friendly way to help you out. That's confusing, but this is user-friendly. You know, it does take a mathematician to do this. So use my techniques to move your knowledge forward. So now we see that we just replaced x with 4/3 to get this. And so that's just what? ln of 4/3, and that's clearly in this interval. So that series is natural log of 4/3. So this is what I was talking about. Once you develop some series, then you can just rig them, so to speak. Oh, well, let me write this in a way so it looks like one of the series that I'm in my list, or one of the series that we derived, and then we have it exactly. Now, of course, this is just a way that Dr. Larson gets you to think about what you're doing. That is, go ahead and think about what these series do and what kind of forms they have. Now, one thing we've noticed about the logarithm deal here, you have to look at the series and think, okay, well, you know, some series, depending on the type of function they are, can converge really fast. Some converge fairly slow. The idea is that when we look at particular series, oftentimes adjustments will be made to the series using identities to make them converge a little bit faster, so that your calculators are more efficient. So again, as you see here, we can work with the series to make it do what we want it to do. We started our series here from the geometric construct at 0, but then we want to match it up with this, so we can start the index at 1, make sure that the plus and minuses are in line, and then adjust these as necessary, and then just figure out from the argument here what this actually needs to be 1/3, that is 4/3, and we're done. So the arithmetic we do is simple, but there's always a reason behind it, okay? Now, what I want to do is to talk about the whole idea behind all of this is that if we are dealing with a convergent power series, the power series must be the Taylor series. So for instance, every convergent power series, is its Taylor series. And what I mean is on the interval of convergence. Outside, we don't know what it is. On the interval of convergence. So if we didn't, and this is a theorem. This is a theorem. Every convergent power series is its Taylor series on the interval of convergence. And that's a major result. So to formally state it here, I'll just show you. This is theorem 9.22. if f is represented by a power series for all x in some open interval I containing c, that is the interval of convergence, then the coefficients are just like we had for the Taylor, the infinite Taylor polynomial. So we don't have to worry that we're not getting this. This says we're getting this. We know we're getting this. The idea is we may apply another technique to get to that convergent series using the geometric series and differentiation or integration like we've done today many times and in the previous lecture, but they always coincide with this. So the idea is, regardless of your method, you're going to get a series that coincides with the Taylor polynomial coefficients. So what I want to do is to look at an example that is devoid of all the beauty of the geometric series and think about this in terms of a Taylor series. So let me move all of this. I have too many sheets here. Sometimes I have to decide what I'm going to keep and what I'm going to throw away. You rewrite notes, come up with new proofs, new examples and things, and different ways to illustrate them, and then you have to decide what you're going to throw away. So let's just think, as I've said before, we can treat polynomials or power series as functions. So we might think, well, you know, if we've got the Taylor polynomial for sine and the Taylor polynomial for cosine, and we could extend those infinitely, and then test what happens to the remainder. Think about it. If the remainder term converges to 0, then we can replace the actual function with the infinite series, with the power series. And so you're thinking, okay, well, if I have power series for sine and cosine, I could just do polynomial division, but that gets a little bit tedious. It's not undoable, but that's something that I want to share with you as a possible way. But say we're just thinking, okay, we're just going to compute some Taylor coefficients. So for instance, here's an example. And this is a fun example. Say we have f of x equals tangent x, not arctangent. And we know that the calculus of the tangent function is not fun. It's no good to us. So for instance, here's something that I've done here. And what I want to do for in this particular example is to write the first 3 terms of the Maclaurin series that are other than 0. So we'll say compute the first 3 non-zero terms of or non-zero terms of the Maclaurin series. So C is 0 of the Maclaurin series for f of x. So again, Maclaurin series, C is equal to 0. You might have a example in WebAssign where they take C equal to 2 pi, you know, something like that. So you're thinking, okay, well, Maclaurin, we'll just say compute coefficients. Now, what we're going to see is that we look at the sine and the cosine, and they're so well behaved, they actually, ladies and gentlemen, have infinite intervals of convergence. And so we're thinking tangent's not in bad shape since it's sine over cosine. So let's see what we can get out of this. So what we want to do is just start out and do some derivatives. So we're going to have f, no derivative. In this case, let me move this over here out of the way. No derivative is just the beginning function. And then let's just go ahead and calculate some derivatives. I'm just going to do the parentheses since that's mainly what we're going to do. We're just going to use that as the first derivative instead of the tick marks. So you're used to this. So now when we look at this, we're going to say the derivative of tangent x is secant squared, not our friend. I mean, it just, we know that it's an increasing function, but we don't get the beautiful derivatives we do with sine and cosine. So the fun is over. So the second derivative, again, we'll just use the chain rule. So we get 2 secant x secant tangent. Of course, the derivative of the secant is secant tangent, so we get 2 times secant to the first power times the derivative of the inner function, which is secant tangent. So we'll clean that up a little bit. So we get 2 secant squared, 2 copies of secant tangent. So as we move through these, I'm just going to put boxes around them. And now we can factor. Let's look at the set. We want 5 derivatives because we can see now that you know, if we evaluate it at 0, that's 0, and that's 0. So we got to have at least 5 derivatives, 5 orders. So we can factor the 2 because it's just in the way, and we'll figure out that at the end. So now we'll take the derivative of secant squared. So that's going to be 2 secant, and then to the first, and so secant tangent derivative times the tangent that's already there. So that's the first part, and now differentiate the tangent. The 2's already factored, so this will be plus secant squared, and then the derivative of tangent is another secant squared. So goodbye to the tangent. So we've got a 2. So we've got 2 copies of secant, 2 copies of tangent. So we got 2 secant squared, tangent squared, plus secant to the 4. And put a box around this. So for this one, we're actually going to get a non-zero derivative because the derivative of secant at 0 is just 1. So we're seeing that the even derivatives are zeroing out. So we've got to pain through this. So you're seeing that we don't have the nice option of a nice integral to get at the tangent function with the geometric series like we have for the inverse tangent. So, you know, it happens. So now let's factor the 2 here again. So chain rule, so bring the 2 down, so that'll be a 4 secant x to the first power. Then we have secant tangent, derivative of the inside, times the tangent that's already there, tangent squared. And now leave this alone and differentiate the tangent, bring the 2 down, so that's a 4 secant squared, then tangent to the first power, times the derivative of tangent, which is secant squared. So that takes care of that. And then this one will be what? Chain rule, 4 secant to the third power times secant tangent in inner function. So let's clean this up. This is kind of unwieldy. But we got a 4 in everything. So that's 4 times 2 is 8. And so we got secant squared, tangent cubed. And here we've got secant to the 4th times tangent. And here we've got a secant to the 4th times tangent, another one. So let's go ahead and reduce this. So I think when I did this, I just combined these 2. Yeah, I did. So go ahead and combine these 2. So this gives us 2 secant to the 4th x tangent x. So that takes care of these 2 guys, plus secant squared tangent cubed. So you see just the derivative calculations that ensue, but what you're going to see with this particular function is that due to the sine and cosine, the convergence will actually be kind of fast. I did a small computation that I want to share with you. And so now let's do the fifth order derivative. So now we're just doing Taylor series, but we're painting through all of this because this is the best we can do. So now we have the 8, which is outside. So now we use the chain rule. So 4 times the 2, that's an 8. Secant to the third x times secant tangent, the derivative of the inside, times the tangent that's already there. Now leave this alone, differentiate the tangent. So we get 2 secant to the fourth times the derivative of tangent, which is secant squared. Okay, that one's done. Now look at this one. Plus, so now we've got 2 secant x to the first power, secant tangent, derivative of the inside, times the tangent cube that's already there. And now leave the secant squared alone. So bring the 3 down, secant squared x. And so that leaves a tangent squared. Derivative of tangent is secant squared. So let's clean this up. So we have 8. We're going to, well, notice, let's see. I've got a 3. Yeah, I don't have any. It's still going to be an 8, but let's just clean this up and see what we have. So we have 8 secant to the 4 tangent squared. Got that, plus 2 secant to the fourth x secant squared. Here we have 2 secant squared tangent to the fourth. That's another one of those, I guess. Secant squared tangent to the fourth. Oh, sorry. Just put this as a 6. I don't know why I wrote that. That's kind of silly. I mean, it's equal, but still, might as well just multiply. Let me scoot this over. So we have plus 2 secant squared tangent to the fourth. And then the last one, we'll get another copy of this, and then we'll combine them. So that'll be 3 secant to the fourth tangent squared. So now this gives us 8. So notice I've got 8 copies here and 3 copies here to give us 11. So that takes care of this and this. And then I have a 6 power of secant. And then this guy here. So when you look at all of this, you're thinking, okay, well, that wasn't a lot of fun. It was doable, but it wasn't a lot of fun. So now we can just write down the derivatives. So let me just pull another sheet of paper here and write down these coefficients, and then we can write the Taylor series, at least for the first 3 non-zero. So now we'll just tabulate them here. We'll start with this one. So what I think I'm going to do is I'll just, as I get to them, I'll uncover them. So here we have f, well, f0 of 0. That's just tangent of 0, which is 0. f1 of 0. We need these coefficients for the Taylor coefficients. We've got secant, so this is going to be secant of 0 squared. So this is just going to be 1 squared, which is 1. And now for the second derivative at 0, well, the tangent of 0 is 0, so that's 1, but 2 times 0 is 0, so we get another 0. Now for the third derivative, that's right here. So that's why I put the boxes around them. So now notice this will be 0 because of the tangent of 0, but that's a 1, so we get 2 times a 1. So this is 2 times 0 plus 1, which is 2. Now the fourth order derivative at 0, because c is 0, c equals 0. We have this right here, this one. So notice we have 8, that'll be 0 because tangent of 0 is 0, and this is 0 too because tangent of 0 is 0. So that's 8 times 0, which is 0. Not a surprise. And now the fifth, let me refocus. Yeah, Zoom is the best. I'm really happy with Zoom. I'm surprised we didn't use Zoom long before COVID. We should have. So now we have 0 here. So notice we've got 8 on the outside. The tangent will give us a 0 at 0. That gives us a 2 times a 1. So we have 0 plus 2 times 1 and plus a 0. So that gives us 2 times 8, which is 16. So now we've got all of our derivatives. So what we can do at this point is say, all right, well, how do we write the Taylor series? Well, we know that in this case, f of x will be f of 0 plus f prime of 0 times x plus f double prime of 0. So this is the Maclaurin series, Taylor series with c equals 0. 2 factorial x squared. So our friends, you know these coefficients. Now I'm doing the tick marks out of habit, so now I use the 3. So much for that. X cubed plus the fourth derivative at 0, 4 factorial. We proved that these have to be the case. That Taylor's theorem proof was long, but it was doable, and it certainly brought these into the light, plus the remainder theorem. X to the 5th, etc. So we're just going to generate, it looks like now the only ones that are going to work, again, because these are all 0. So this one's 0. And notice we're going to get just a bunch of positive terms. So now we have 1 times x plus, well, again, 0, 0. And here we've got 2. So we have 2 divided by 1 times 2 times 3, x cubed. So we got all these. And then the fourth derivative at 0 is 0. And then the fifth derivative is 16. So 16, 1, 2, 3, 4, 5. Always factor the factorials. That way it's easier to compute, etc. So this gives us x plus, well, of course, the 2's absorb. So we get x cubed over 3. And here, notice the 2 and the 4 absorb to give us a 2 here, and then the 15 survives. So that'll be plus a 2 over 15 x to the 5th. So if you want, and it doesn't matter, let's just kind of move this to the side so it looks like the other term. So this would give us our first 3 non-zero terms of the Maclaurin series for tangent. So again, we had to work harder here, but now we're seeing in the previous section in 9.9 that we have whatever we can use, the geometric series and calculus. And now as we move into the section 10, we're seeing that, okay, well, all of those series are actually Taylor series. And since we can't really use, in this case, as I said here, we can't use anything geometric here because we don't have the calculus to support it. We just work with the Taylor coefficients. And the tangent function is not fun, doesn't have easy derivatives. They're doable, but they're not easy. And so now I wanted to take this and just do a simple calculation. So, you know, how does our calculator work? Well, we know. So for instance, say you're in a physics class, and I know you've got your fancy $300 calculator, or maybe your Walmart calculator that didn't cost you $300. And you're saying, okay, well, in my physics problem, I need tangent of 5 degrees. Now, of course, if we're using radian measure, then we'll convert to radians. And we'll say tangent of 5 times pi over 180. And when we do this, the 5 will absorb, so we get tangent. We have a pi. So 5 into 18, that'll go 3 times, and then into 30, that gives us 6. And so you're thinking, okay, this is really what your calculator's doing with an infinite series like this. And so now you're thinking, okay, well, this will be approximately, let's go ahead and substitute, pi over 36 plus 1/3 pi over 36 cubed plus 2 over 15 pi over 36 to the 5th power. Now, what I did in this case is I just used my Google calculator, the free Google. So let's go to free Google. Let's see, I have to move this over because it won't see it otherwise. There we go. I use this in my pre-cal when we get our calc. I always tell them calculus approximation, kids, it's time for a calculus approximation because of course they don't have calculus yet. So we can do, again, we're, in this case, we're in radian measure since I've already done the conversion. So it doesn't matter anyway. So we've just got what, pi over 36. So we'll say pi divided by 36 plus, now we'll have 1/3 times pi over 36 close, and we'll raise to the 3rd power. This Google calculator is nice. It's easy and it's free. Plus 2 divided by 15. It's great for teaching inverse trig functions. It's been a blessing. One of my honor students told me about this thing, and I thought, wow, I should have been using this earlier. And we've got pi divided by 36 raised to the 5th power. And this gives us, I'll write this down, 0.08748866143. That's amazing. The calculus could give us this, and computers are good at arithmetic. And now let's just see. What if we said, okay, so maybe you're in physics class and all you had was this formula, and then your friend says, oh, well, I'm going to use my calculator. So we'll go to degree mode, and we'll just do tangent of 5 degrees. Look at that. So the exact, at least with a nice calculus approximation, we have tangent of 5 degrees using the Google calculator gives us 0.08748866143. 8, 8, 6, 6, and then it starts to change 3, 5, 2. So I'm not joking. Calculus is the sophisticated arithmetic that makes our technology work. So now we see in this case, not bad. So the idea here is that now you're at the point to where you're actually understanding mathematics, that analysis is sophisticated arithmetic. Why can we do the calculations that we do? Well, necessarily we have the beautiful technology that a lot of you all will use in your STEM careers, but we have calculus, we have analysis, and that's why any of the calculations make any sense at all, because the calculus is what really provides the ingredients to why we do what we do and how our system works. So as you study medicine or dentistry or computer science or engineering or mathematics or physics or whatever, all of the math becomes your language. And so, like I said before, the physicists always say, well, physics is the mother of all science. And I agree in a lot of ways, but physics would be nothing without the mathematics. Remember, Sir Isaac Newton was a Renaissance man, but he was a mathematician first. And his work in all those different fields was made exceptional by his genius in mathematics. So now hopefully you're gaining an appreciation of this. And so what we have left to do is just maybe look at a few remainder terms to see what happens. So the final result, the final theorem, just in closing, everybody, you've been very good, will just be the convergence of Taylor series. And basically what that's going to mean is that if we can show that the remainder term converges to 0, then we have a really nice infinite series that converges to the function. But when we can't do that, we have to try other means. So now hopefully from today, you see that the convergent power series in the interval of convergence is its Taylor series. So however we go about finding the convergent power series, it will always correspond to the Taylor series. And here we had to use Taylor directly. And look at the excellent results that we got. Okay, so again, thank you for your attendance today. I hope you're enjoying this. I do believe firmly that if this appeals to you, then you are in the right place. There's one thing about mathematics that should just give you a thrill. And when it means that you understand how that little device that you've been using probably since the second grade works, now you can share with your friends that, oh, here, let me show you a few calculations to give you some insight as to how that calculator works. Now, if they're not STEM people, they may not be interested, but they're certainly going to be impressed. So thank you for your attendance today. Good luck with your studies. If I don't see you in my office hours, I'll see you next week. Again, just stay focused on your work, write your good mathematics, keep yourself entrenched in the exact calculation, and use your Google when you need to get a nice approximation. So everybody have a great day. Thanks again.